Hi, I'm Princess Senate, conference producer at Technology Networks, and I am here to introduce our final talk of the day towards robotic laboratory automation plug and play, the LAPP reference architecture model. Joining us today is Adam Wolf, senior engineer from Takeda. Adam's background is in mechatronics and robotics, with a focus on laboratory automation robotics and corresponding integration frameworks. He leads global proof of concept projects within Takeda's R&D while working on his industrial PhD and leading the SILA Consortium's robotics working group. A warm welcome to you, Adam. Following the presentation, we will have a Q&A session and we welcome any questions that you may have. Please ask questions using the Q&A system to the right-hand side of the video player. And without further ado, I will now hand over to Adam to begin his presentation.
Thanks a lot, Princess, for the kind introduction. Hi, everyone. I'm Adam Wolf, and today I will speak about the topic of supportive lab robotics, and more specifically, the framework to make their integration more easy. So first, I will take a general overview on the present landscape, how supportive robotics in lab automation are used, and then proceed with the proposal, what the laboratory automation plug and play framework is all about, what are the components and the aspects to it. And then finally, I will present proof of concept studies, first in the consortia and academia segment, and then turning to more technologically mature implementations in the form of pilot projects in the industry at Takeda. So first, let's review an overall landscape of supportive lab robots. And for that, we created sort of like a systematic visualization with a two-dimensional matrix. On one axis, we represent what we want to use the robots for. So whether we want to get some data from the lab via sensing, or whether we want to actually manipulate something in the lab with actuating. The second axis, the vertical one, represents whether a human is directly controlling the robot by doing so, or whether it's autonomously executing a sequence. So let me zoom in. It's quite a crowded figure. We will begin with actually the first segment. That's the remote inspection. And what that means is the robot is equipped with a certain type of sensor. In most cases, it's an RGBD camera. At least that's what we were experimenting with the most. And the idea is to let a remote user, a standby worker or a lab expert from across the globe from a different location, to take a look at a specific laboratory unit operation. Maybe there was an error, there was an alarm triggered, and we want to know what happened. So one would log in to a web interface, drive the robot to the location where the error occurred, and use the camera or other type of sensor to acquire some data and information about what happened and whether an actual in-person deployment is needed to resolve the error. The second segment is when we do it autonomously. So the robot does the same, acquires data, let's say visual data about a lab operation, but this time the path that it covers is pre-programmed. So you can have points of interest in the lab defined where the robot would, in this case, take a picture and transmit that visual information to a computer vision algorithm to detect anomalies or actually just to track the status of the lab. There can be different use cases in this regard. This segmentation example on the bottom left you see is just one example where objects were detected and localized on the picture, and the semantic interpretation of the scene resulted in detecting anomalies in the workflow. The third segment is an interesting one. It's a combination of the remote inspection capability with actual manipulation capabilities in a human-controlled fashion. So that means that someone is controlling the robot, seeing the visual feedback from the robot, but is also capable of moving the arms of the robot to intervene in the lab process if needed. If there is an error, again, the same use case, you would not just be able to assess what happened, but use the arms of the robot to actually resolve a physical error if it's possible. So for that, a student project was focusing on creating a virtual reality-based cockpit, a virtual cockpit, where the user saw a three-dimensional stereoscopic image in the middle coming from the stereo cameras of the head of the robot, and also the wrist cameras for fine manipulation tasks. And with the virtual reality controllers, the user was able to relatively move the robot's arm in fine precision and manipulate objects. So there was a series of tests conducted to assess the usability, and lab users were capable of driving the robot and performing this basic manipulation tasks. It's important to mention at this point that on each slide, you see these red TRL numbers. So that refers to the technology readiness level of each project that we conducted. And you see here, it's TRL 4 out of 9. So that means it's a prototype development, but not for an operational use case. So this is not yet for real life utilization in the lab. It was a feasibility study. And that's actually a lot of what we do in our team. We work on new emerging technologies and look for ways to deploy them in actual lab use cases. And now the final fourth category, and the biggest one, the most important one, and also the most mature one, is of pre-programmed workflows. So this means that the robot does something in the lab actively, performing manipulation, and does so in a pre-programmed sequential fashion. So this is how most robots actually operate. Also in other domains, they have a program, a motion sequence that they perform, and that does something in, let's say, the manufacturing process. But here in our case, of course, it's nothing like that. It's more the laboratory tasks, such as lab transportation. That's one of the biggest use cases. Robots do that both in a stationary benchtop setting and in a mobile setting. So the latter is a relatively new field, gaining coverage in the laboratory setting, but also introducing a lot of complexity. And to that, I will talk in more detail later. But here I also want to mention another use case, which is sampling with the robot. So basically, in a laboratory, let's say biologics process development laboratory, common use case is having to take samples from different unit operations, let's say a bioreactor or any other instrument. And for that, normally a human would need to go attach the sampling syringe or any other container, pull the sample, seal the line, take the sample to analytics. Now, what we looked at, and here also you see relatively low technology readiness levels, meaning that this was a proof of concept study. We looked at tube welding and how we can robotize it. We did that with custom-made 3D printed end effectors, robotic fingers, that were capable of grasping the tube from a fixture and loading it to a tube welder and starting the welding process. And then the next step that the Japanese colleagues were looking into was to actually draw the sample with the syringe, and that needed a custom actuator, in this case, a custom end effector. So this much about the general landscape of supportive lab robotics. And as I said, I want to turn more attention to a specific segment of that, which is mobile manipulation in the lab. So when we speak about mobile manipulation, it's important to distinguish between two different sets of lab operations. One is high throughput use cases where there are routine tests and repetitive workflows. And usually these are robotized with highly customized, purpose-made robotic cells, which can operate in setup and leave or even lights out fashion. And contrary to that, in R&D laboratories and process development laboratories, more flexibility is required. There are dynamic workflows, standalone equipment that's often not robot friendly, but designed for human operation, which means that still there is a lot of manual work included with these processes. To bridge the gap, collaborative and mobile robotics are emerging in also other segments, but starting to gain coverage in the lab scene because they can operate in human designed environments. And that means less structured environments. So the location of the units change. They have to interface with an array of different variety of equipments and do that together with humans in cooperative or collaborative operation. So when we put a traditional stationary robot, like you would imagine an industrial robot, next to a mobile manipulator and compare them to humans, we see that mobile manipulators are sort of in the middle ground in terms of throughput. And this means that they won't be as fast as humans and won't be as fast as stationary robots by any means, but they have a higher availability compared to a human who can work maybe an 8-hour shift. And during the night, the robot can take over and keep the processes running. The flexibility is the middle ground, again, between stationary robots and humans. A stationary robot is good in structured, repetitive tasks, and the MoMA is a bit closer to how a human would operate in the lab. So with this in mind, we had a specific use case in the lab. Here it's detailed. We had an object of interest that we wanted to transfer between different devices in the lab. And this was a standardized container, an NC SLAS conform, also known as SBS microplate, that is usually fed into lab devices, liquid handlers, analytical devices, storage devices at fixed handover positions, also known as sites. And there are fixtures to hold the piece of labware, that the microplate, that allow a tolerance for the robot to insert it with still relatively high accuracy needed. So that's why these applications need optical markers, so-called landmarks or fiducial markers, to aid the robot with detecting this handover position, especially for mobile manipulators. So in our case, the pickup and drop-off locations need to be defined by a means of parameter in the command, because our workflows are dynamic, as I was referring to, how it is usually in R&D, and we need to reconfigure it depending on the requirements. And also the robot will need to navigate between not only different stations, but different laboratories and even different floors. So there is a lot of complexity that goes into it, and I will go into those topics in more detail. When we started looking into this use case, we assessed, of course, what's out there on the market in terms of mobile manipulation for lab automation purposes. And it appears that there is already quite a landscape of solution providers who have different platforms. These have a lot in common. All of them feature an autonomous mobile robot, AMR base, which is capable of autonomous navigation, localization, and mapping. And on top of that, the integrators mounted different types of robot arms, either 4 degrees of freedom SCARA robots or 6 to 7 degrees of freedom articulated robot arms. And what's also common that I was referring to earlier is that they all need an additional perception system to detect the fine positioning of the handover site. And that's why the reason behind that is that the mobile base itself has an accuracy maybe in the centimeter order of magnitude, but I was already referring to the accuracy that's needed for inserting the plate in the fixture being in the millimeter order of magnitude. So to bridge that gap, you need to localize the position. And most of these solutions do that by vision using fiducial markers, but there are also examples with tactile probes and tactile sensing. So these robots all feature custom end effectors that are suitable for the manipulation of microplates. And that is pretty much a standard anatomy that they share. And what they also share is the fact that they are complex systems. So the AMR is one module. On top of that, you are mounting a robotic arm, a vision system, a control system, and you need to integrate that with the rest of the lab ecosystem. So the scheduler that orchestrates also the lab instruments, there need to be a communication protocol, and these are a lot of sources of errors, a lot of interfaces, a lot of layers. So to answer the challenge, we started working on a proposal that I want to introduce today. And this is the laboratory automation plug and play framework, which is intended to serve as a reference architecture model. So the motivation behind it really starts with what we can, what we want to standardize in the lab. And that itself starts with the bottom, with the physical layer, the process layer itself, where the containers and the physical aspects of the process are partly already standardized. So I was referring to the SBS microplate as an example. And that already makes it simpler for the instrumentation layer to interface with the physical objects. And by the instrumentation layer, I mean the lab devices. So that is the analytical devices, the pipetting robots, but also the supportive lab robots that connect these units with each other. And as I mentioned, through the physical interfaces like the standardized gripper, these two layers can interact physically. Now, talking about the assets in the labware and the instrumentation, it's important to mention that to maximize the ease of integration and aim for plug and play integration, we need to represent the relevant pieces of information about each asset in a standardized and compatible data structure, or so-called ontology, to enable a master control layer, an orchestration layer, or scheduler layer to actually control the process. The instrumentation layer is the one that the orchestration interfaces with via, in the best case scenario, via a standardized communication protocol. And by standardized, I mean an open protocol that is not proprietary, documented, and free to use. Of course, there are proprietary protocols, but that's exactly where we want to get away from and strive for standardization in all of the aspects that I am presenting right now, also including the process programming aspect to represent the workflows in a standardized fashion that's transferable between different laboratories and has a suitable level of abstraction to do that. And of course, ultimately, we want to have an uplink towards a laboratory information management system because we want to get the data out of the instruments. And the data format itself is certainly something that we need to standardize. And there are already initiatives to do that. The problem with the present state is that these systems are becoming increasingly complex. And it's a fairly heterogeneous system architecture that we are dealing with. And of course, this poses a barrier for implementing these systems. So what we propose is, with the laboratory automation plug and play concept, to create a holistic and agnostic reference architecture model for covering the whole vertical of the laboratory automation ecosystem by outlining the canonical layers and components in the integrated system and the control architecture, and also allocating existing building blocks for different aspects and creating an overarching blueprint how to combine them or how to extend them with additional components to achieve a standardized communication between the components and also create the standardized information representation aspects that I was referring to. So this is exactly what the lab concept itself, and this is something that we published in scientific papers, that the lab concept outlines. We have a hierarchical decomposition of the robotized lab workflows, a multi-layer control architecture, and these two are mapped against each other. And also the information model in the form of a digital twin, a device-centric information representation to achieve ultimately, in the case of supportive lab robots, a teaching-free plug-and-play integration of the lab devices. And then, of course, communication protocols that I was already referring to. And on the bottom, you see how this endeavor was addressed by the means of a series of projects, first starting with the early technological readiness level in the form of the concept proposal, and then creating academical proof of concept studies, and then working towards the industrial implementations that I will present at the second part of the presentation. But first, let me draw your attention more to the concept itself and start with the hierarchical decomposition of the lab workflows. And that really starts with looking at what a specific lab provides as a service, a set of services. So be it like high throughput screening or microscale process development services. This is a bunch of experiments that the specific lab setup can run, conduct, or execute. Experiments, could call them assays or procedures, like chromatography, parameter optimization run. And now we arrive to a layer that's already hardware specific. So the task level is a device level elemental action item. And here you see that I already split the columns into one device type, which is liquid handler, and another one, which is supportive robotics. And for each, they put besides each other how each level is represented. And for the rest of the talk, I will focus on supportive lab robotics. That's what we elaborated the concept for primarily, but it's really agnostic. So in that case, the task and subtask levels are the ones that are relevant from the system orchestration layer. So these are device level activities. For example, for the robot, it's a labware transfer activity to take a plate from one device and put it to the next one, source and destination. And how it's broken down into subtasks, picking and then placing it is the next step, level 4. And then come the low-level parts that are, in most cases, masked away from the lab orchestration layer and dealt with by the low-level robot controller, middleware, or even the embedded controller that I will present in the next slide. So these are the motion sequences and motion primitives, and ultimately the joint level actuator primitives. So how it maps against a system architecture is the following. On top, we have some information management system or electronic lab notebook where we want the data to be accumulated from the different services. And for the execution of the assays, there is usually a scheduler or laboratory execution system that runs the procedure and breaks it down into tasks and subtasks to control the device level control units. And these are, in most cases, dedicated PC machines. And on the bottom, for the really low level hardware side execution, there is the embedded controller. So there is some microcontroller in most devices and robots integrated, or a programmable logic controller that implements these really hardware specific parts. So staying with supportive lab robotics and the labware transfer task, let me introduce you to this graphical representation of the breakdown of a specific labware manipulation task, the labware transfer. And to that also belong some vegetative activities, let's say, that are needed for the robot to maintain its state. For example, to monitor the battery status or to provide a teaching interface for someone who wants to teach the robot from the scheduler side. But the most important one, and that's the one that's usually exposed, let's say via SILA interface, standardized laboratory automation communication protocol, is the task and subtask level activities for the outcome-oriented task. So that means the labware transfer itself is parameterized by really just the source and the destination location, and maybe a labware type or labware ID. And it's broken down into picking and placing, and also letting the source and destination device know when to prepare for input or output. What's below that, and this was also visualized on the previous tables, the low-level part, as I said, is masked away from the high-level controller, from the scheduler. So this is already, well, from the robot's perspective, from the perspective of the components of the robot, the arm, the base, and the gripper. And it's the robotic middleware that control the motion sequences. Now, arriving to the second aspect, the ontologies, I want to introduce what we consider the most important piece of information for supportive lab robots, the relative hierarchic representation of frames of references. So basically, positions within the context of the asset. And this asset can be a piece of labware or a piece of lab equipment. In each case, we need to represent the position of the previously mentioned optical marker that the robot can detect and bind to its own coordinate system, and the frame of reference for the handover site, where finally the robot needs to place the labware and ultimately align the frame of reference of the labware with the frame of reference of the handover site. So how it looks in more detail and more visual representation, how it's connected. Here you see with green represented what we call the digital twin instance of the device. So in this representation, you see the relative positions in the context of the device between a device coordinate system, the marker, and the handover site. So the robot tracks its own configuration with kinematics and motion control, and also navigation. And when the computer vision functionality kicks in, that's when the robot can bind the reference of the device with its own coordinate systems. But let me switch to the next slide when this hierarchical representation is visualized from a different perspective. So here you see how the coordinate transformations are connected. So basically, in each case, the robot localizes itself with relation to a map of a room, and there are different stations located on this map. And at each station, there might be an array of devices, each device having its own array of sites where the labware can be located. And the robots need to drive to the first station, localize itself inaccurately with relation to the map, but then accurately detect the marker position with computer vision, plan the motion from the tool center point of the end effector to the pickup site, get the labware to the tool center point, position it on the onboard storage or hotel, then navigate to the next station with simultaneous localization and mapping in the centimeter accuracy, pick the plate from the hotel, detect the marker of the second station, do the motion planning again, and finally place the plate there. So this is in sequence how the digital twin concept comes together, how the hierarchic representation of the positions is implemented. So to create proof of concept studies, we took existing building blocks for specific aspects of the ecosystem. And as such, I already mentioned standardization in laboratory automation, or SILA in short. I'm wearing my second hat besides Takeda with the SILA consortium as the lead of the robotics working group. And as such, I wanted to also talk to this topic. SILA as a consortium is a not-for-profit membership organization. It provides a platform for exchanging and collaborating on the development of the standard itself, and that's the core working group, and on the development of domain-specific guidelines and feature definitions. That's what we do at the robotics working group. The standard itself has 3 layers: the specification, conceptual one, a technical one, and then a domain-specific collection of features. From the technological perspective, it's a service-oriented interoperability protocol where a lab device, or as a matter of fact, also a lab robot, is considered as a service provider that implements a set of features. And the service consumer is considered as a client that triggers specific commands as part of these feature definitions. And when I say feature definition, there is a framework within SILA called the feature definition framework that serves as a semantic representation of the capabilities of a SILA server or service provider. And it serves as a contract between the server and the client. So it's important that we standardize also these semantic representations to achieve plug and play compatibility. And that's one of the key goal statements of the robotics working group, to work on standardized communication, especially specifically for robots, mobile and stationary robots in laboratory automation scenarios. Again, rely on existing technologies, extending the SILA stack where necessary, and also facilitate exchange between device vendors, robot vendors, integrators, and users. So this is a community effort that we work on the feature unification for the labware transfer feature and for an extended taxonomy of additional robot capabilities, and also on reference implementations, such as the bridge between SILA and the robot operating system, or a reference implementation for the labware transfer controller for stationary robots. That was a subject of hackathon in the past with BioLego, co-organized with SILA. And now currently we are looking into standardizing this also for mobile manipulators. And we have subgroups. Sometimes there are breakout subgroups working on specific pieces of technology. And one example was focusing on ontologies. There we started at Endeavor to set up a labware ontology. So this is a work in progress, as a matter of fact. Now, speaking specifically to the reference implementation for standardized stationary labware transfer, I want to introduce a setup that we created in the course of one of these hackathons. 2 types of robots, both stationary benchtop robots, connecting to storage units and a plate reader as an exemplary workflow, a set of sensors and actuators, an embedded controller for each robot, and also for the plate reader, a device level controller, and on top, a scheduler. So here you see the same canonical layers that I presented earlier towards the beginning of my presentation. And this was taken then a step further by an academical partner of ours, the Oberlin University, where a mobile manipulator, a ROS-based mobile manipulator was used. And basically, the building blocks that I presented earlier were put together. The building block of the SILA ROS bridge, which was also subject of a previous hackathon. And here you see a technical outline of this bridge. This means that SILA is responsible for the high-level scheduler side of communication, while ROS is responsible for the low-level, the robot-specific communication. And the bridge implements both a SILA server and a ROS action client, service client, or topic interface, depending on what low-level robot interface is available. It's important that throughout this exercise, we created a table where we mapped the concepts of the Scylla ecosystem against the concepts of the ROS ecosystem. I won't go into more detail on that for the sake of time, but just for example, an observable command on the Scylla side is implemented in most cases as an action on the ROS side, because this is an activity that typically takes a bit longer and you want to get continuous feedback from the scheduler's perspective also. So the reference implementation at the Oberlin University also addressed similar workflow as we did with the stationary robots, and utilized again the canonical layers of the system architecture. The device level control layer was the most interesting one. There we implemented the Scylla-ROS bridge and also an interface to the digital twin of the devices to get the positions that I presented earlier. On the next slide, we see a visualization of the previously presented breakdown of the task, but now mapped against the actual technologies that were used to implement them. So you see the top two layers, the task and subtask layers, were implemented with Scylla concepts. The subtasks specifically by the means of Scylla commands in the unified library transfer feature definition. And the low-level functionalities, the motions, were implemented by the means of ROS functionalities. And this is what I said that's masked away from the scheduler. So this is the final result of that study that the university conducted. In the middle, you see a visualization of how the robot perceives the world, detects the coordinate systems with the computer vision solution, and also uses the map to navigate from station to station. And now let me proceed to the more mature reference implementations, or I would say the pilot projects that utilize the same concepts, but now in an industrial setting. So at Takeda, we have use cases in the lab with a set of lab devices that we wanted to automate and integrate with each other to have an end-to-end workflow. And to do that, for the sake of flexibility, we decided to use not stationary but mobile manipulators. First, only one of them, but then potentially combining multiple different ones in one system. So here again, you see the layers of the system architecture with the scheduler on top, the device level controller, and then the low level hardware side control. And in the case of the MoMA, you see what I meant at the beginning when I said these are complex systems in themselves. The MoMA has a built-in controller, the interfaces, the vision system, the arm, and the base. So in our case, there was a selection of specific devices and interfaces and robots, and also middleware for the robots. It was based on Omron components, an autonomous mobile robot and the collaborative robot arm integrated by Angretech and controlled via Scylla by Green Button Go scheduler from Biosero. So this is an ongoing project. We are still working on figuring out the actual system architecture to cover all of the complexities of the landscape, and also considering scalability and future extensions. And there we arrive to the future state where we will have multiple robots from different vendors. And we want to initially set up separate systems, separate scheduler instances, but eventually combine them into a fused overall integration platform with the help of an overarching orchestrator and transportation layer. So there are really some intricacies to that, figuring out which component is responsible of controlling the elevator, Is it the fleet manager? Is it the middleware? How we can bring together the two ecosystems to form finally one functioning and in an optimal manner functioning system. Finally, to close my presentations, I want to present a few videos, starting with how we started during the planning with computer-aided design-based simulation from Agrotech. And this was used also for the sequence that I presented for the hierarchical position representations. So here you really see just a benchtop transportation. But the next one is a more, I would say, fancy one. Here you see the robot actually interface with an automated door and then arrive to an automated storage unit, again, using the computer vision system to detect the handover site, load the microplate, and then arrive to the next interesting feature, the tool changer, where you can swap the end effector for a different one. And instead of microplates, this time be able to manipulate Petri dishes. So here I will stop when it picks it up, but I think you get the benefit that this tool changer provides with in terms of flexibility. So finally, the actual site acceptance test looked like this. When the robots performed in the lab, same sequence from one bench to the next bench, and successfully done so also in a looped fashion for stress testing. And this is where we are right now. We are taking a step-by-step approach towards achieving the overall integration architecture that I presented as a concept. We do that from bottom up. So on top of the robot middleware, we will implement the standardized Scylla interface and connect it to the scheduler and then to the orchestrator. So at this point, I want to say thank you to everyone who was involved in all of these projects, primarily my colleagues at Takeda, my teammates, and also my colleagues and supervisors at the university and at Scylla in the robotics working group. And last but not least, also the partners who provided the components and with whom we worked towards the implementation. So if you're interested, you can check out some publications, the scientific papers that I was referring to on this link, and also some earlier publications that we uploaded. So with that, thank you very much for your attention, and I'm looking forward to the questions.
Thank you very much, Adam, for that fantastic talk. I am aware of the time that we have left, so I'll dive right into your first question, which is, what technical and organizational challenges do you see against the adaptation of the vision?
Thanks a lot for the great question. I think to the technical aspect, I was really trying to speak during my presentation. So it's really in the complexity of these systems, figuring out the appropriate interfaces and system architecture. But the mostly challenging aspect, I think, is an organizational one or cultural one, I would say, which is the mindset of each stakeholder that we need to change, honestly, to make everyone adopt the standard, and especially the device vendors. And it's quite a challenge for them. Also to change partly the business models, coming away from the proprietary standards and introducing standardized ones. But I think it's important to consider that complying with the standard can also open up new possibilities for solution providers, gaining more coverage with a broader user base, which ultimately can be a unique selling point.
Thank you, Adam. That's great. That's a great answer. We do have some time to answer one final question for today. How does the laboratory automation plug-and-play framework address the increasing complexity of robotized laboratory automation systems?
So that's really, to summarize, I think, a great question, and thanks for that. In conclusion, the laboratory automation plug-and-play system aims to break down the complexity of these systems by outlining the different components and layers of the architecture and basically outlining a blueprint, a conceptual but still agnostic blueprint that should help integrators, users, and solution providers to utilize the benefit of plug-and-play compatibility.
Thank you so much, Adam. Unfortunately, that's all the time that we have for today. Any questions that we didn't have time to get to will be sent to the speaker after the event. As with all the other talks in the event, this talk will now be available to view whenever you want for the next 30 days. That just leaves me to say thanks again, Adam. And for everyone watching, we'll be back tomorrow at 8 a.m. Pacific for another fantastic lineup of talks. Goodbye.
Thank you very much, Princess, for facilitating, and thanks everyone for the attention.